So welcome to this pre-recording of the lecture on representation of expressions in this course on symbolic computation. So an expression consists of operators and operands. Expression trees are not binary. In general, when we look at symbolic expressions, when we look at evaluation, we distinguish between numeric and symbolic evaluation. With numeric evaluation, we apply the numerical elementary operations, and they are binary. So that's why we get to binary expression trees when we look at numerical evaluation. Not so when we look at general expressions. Okay, let's look at a mathematical expression, our favorite mathematical expression, a polynomial in several variables. Here a particular case, or a general case, so it's always a finite sum in a finite number of variables. So we have m terms, n variables, and the coefficients belong to some set k. So this is a polynomial written in mathematical notation. Now, if you look at this mathematical notation, we see the big sigma, which is a sum. So that is the first type of operator that we see. This big sigma is also a loop, a for loop. So the index I runs from 1 to m, runs over all the terms. So that is already an indication that the operator sigma has actually a list of operands. It's binary if the m equals 2, but in general the m can be anything. So then we have a product of a coefficients times a monomial. So that's already one product, that's over here. But then you have the big pi. This is the symbol for the product. Has nothing to do with the pi, the symbol pi for the area of the unit circle. No, the big pi represents the multiplication operator, and also that operator has a list of operands. So this is also, if you like, in computer science terms, it is a for loop. Then what are the factors in this product? Well, this leads us to the third operator. We have the power or the exponentiation. So we have the natural degrees, so the integer powers, or the numbers that represent the powers of the variables that occur in each monomial. So the point that I wanted to make is that except for the exponentiation, which is binary, the addition and the multiplication operators, they do have lists of operands. So the expression trees in general, of general expressions, will not be binary. So this can be immediately seen from the mathematical expression, so that's rather hard. Let's look at the expression tree, a concrete example. So we will work with this example in the demonstration in a Jupyter notebook with SageMath as kernel. So we have three terms. I limited to 3 because of the size of my slides. And you see there are 3 children under the root. The root has the value, the operator plus. So you see that the minuses are pulled into the coefficients. So we don't do minus 35 over 2, but actually we add the coefficient minus 35 over 2. We multiply this with the factor. So not only the addition has multiple children, but also the product, also the multiplication operator, has several operands. So the leaves are either the constants or they are the variables. So we see this tree in computer science from drawn backwards, upside down. One can also see that the leaves are the input gates when we evaluate this expression. Okay, when we evaluate an expression, we can do this in two ways. We can do this numerically. So numerically, the inputs, the variables, are replaced by the numbers. So in numerical evaluation, the input are the numbers for all the variables that appear in the expression. The result is then also a number. Very straightforward. In the symbolic evaluation, the variables in an expression are replaced by symbols. So in that sense, the result is then also an expression. And of course, one can do some hybrid numeric symbolic where some of the variables are replaced by numbers, some of the variables are replaced by symbols. Okay, so this is the important distinction, what you can do with the general expression. With the general expression, one can evaluate that expression symbolically. We will talk about substitution in a later lecture. Substitution is a very powerful operation. How come we had the binary expression trees then when we looked at fast callable objects? Well, when you do a numerical evaluation, you apply the elementary numerical arithmetical operations, such like the exponentiation, but also the addition and the multiplication, they are always operating on two operands. So here you see the binary or one potential binary evaluation if you evaluate from left to right. This is one binary expression tree which represents one evaluation algorithm for this monomial. Okay, that for the concepts, mainly expression trees. So what I will try to demonstrate now with the Jupyter notebook in a kernel of SageMath is how this works, how you can actually explore and experience this in a Jupyter notebook. Okay, so let me start from the beginning. So I have a completely worked out Jupyter notebook prepared, and I may actually need this if I want to steal some, if I blank out at some point. But the purpose of this pre-recording is also that you see the step-by-step build-up of a Jupyter notebook. So we explore expression trees, symbolic and numeric evaluation. So this is the recording, the notebook for my recording. Okay, so let us look at expression trees. So our favorite expressions are polynomials. So let us look at a polynomial in three variables. And the names of the variables are x, y, and z, of 3 terms of maximum degree 13 and with rational coefficients. Okay, I will use the random element for this. So first I will define my polynomial ring, so QQ, and then, so that's the capital P. Perhaps let me again explain the syntax here. So with this assignment, so QQ is the abbreviation for the set of rational numbers. So what is at the left side is what I choose. I choose the name of the polynomial ring, so that's the capital P, and I choose the name of the variables x, y, and z. So you see how SageMath confirms this. I will have the little p, which will be a random element, but I will set the random seed to the year in which I'm executing this. So this makes that I will always have the same random polynomial. So the degree is 13 and the number of terms equals 3. So this is, by the way, also the polynomial that was on the slides. So I practiced this a little bit. So I wanted a polynomial that was interesting enough. And once I found the right polynomial, so I played around with the degree equals 13 parameter. Because you see that, well, we do have actually a degree 13 term here. Okay, so operator and operands. Now I cannot, the methods, so there are methods on expressions. Now it is important again to realize that this polynomial, that is P, is actually a multivariate polynomial, and it belongs to the library of singular. So singular is a very important component for computational algebraic geometry in Sage. So we need to convert this to a general expression. And how do we do this? Well, think about this for a while. But we've seen the symbolic ring. So the shortest way to convert P into an expression would be, or is, to cast. I will not put cast again in italics and emphasized because it's not the highlight of this lecture, it was the highlight of the previous lecture, but I will indicate this anyway, is to cast P into the symbolic ring, and that is abbreviated by S and R. But for this lecture, let us apply symbolic evaluation. I will declare variables or symbols x, y, and z, and then evaluate P at those symbols to make an expression Q. So there's one statement that is going to come out of this. So I first described what I did. So I will make Q, which is P, where I replace, wait, I'm still going too fast. I first have to declare my symbols again, the X, Y, and Z. So the X, Y, and Z are now general variables, and now I can replace the variables that was used in P with Q. So let me make it clear that the Q will belong to the class symbolic expression. So observe the statement, the symbolic evaluation. So the letters X, Y, and Z are in this polynomial at the left hand side. You can consider them as formal parameters in a function. So when you have a function that you evaluate, there are formal parameters in there. During the evaluation, there is the assignment of the actual parameters to the formal parameters. So what is at the right hand side of all these equations here are the new symbols, the general symbols that I just declared X, Y, and Z. So that is an example of an application of a symbolic evaluation. And why did I again do this? Well, I can ask for the operator. So, and the operator is an addition, and I can ask for the operands. So here you see the list of operands. So, and I can continue this. So what is important is are the methods operator and operands. So let me select from the list of operands the first operand. So I'm retyping operands now. And it is operands in plural. So you see that I have selected the first term, and the operator will be a multiplication, and the operands are the powers of the three variables. Let's continue. Let me select the first operand. So I'm started counting at 0. So we had three operators: the addition, the multiplication, and the exponentiation. So here we have the binary operator pow, which takes the variable name x and the exponents on input. So what I will be using will be the labeled ordered tree to visualize. So the labeled ordered tree will be used to construct the expression tree. So I can do this top down or bottom up. So let me do it bottom up here. So I have the leaf labeled ordered tree. So it's a leaf, it has no children. The label is x. So let me just see if I'm doing this right. So I just have the leaf. That's how it gets represented. So then I have another leaf, which is the power. So I'll call it leaf 5. And let me make the node x5. So this stands for x to the power 5. So this has two children, leaf x, leaf 5. And now the label is the hat, which shows the exponentiation symbol. So here is the representation of my first tree, x to the power 5. The next monomial, you can actually see it here on the slide still. So it's y to the power 6 and z to the power 2. So let me be a little bit robotic in the sense that I will first make the leaves for the remaining two symbols. So I have the labels y for leaf y, and then I have leaf z. Then I have the powers. I had the exponent 6 in y to the power 6. I had the exponent 2 in the labeled ordered tree with label equals 2. Okay, so I have my instructions for the leaves, and perhaps I can insert, well, will not insert. So I have the node y to the power 6 labeled ordered tree that has two leaves, so leaf y, leaf 6, and it is the power, and I have node z2, which is the labeled ordered tree, leaf z, leaf 2, where the label is again the exponentiation operator. Okay, so I miss actually one term, so that's the coefficient 1/2. So let me make that leaf as well. So that's the, I will call it the coefficient 0. And the label is -1/2. So then I can make my monomial. So the monomial, perhaps let me shift here my slides a little bit. So this is the monomial that I want to make. So I have a node, so the first term, so that's term 0, is the labeled ordered tree. I have the constant, so let me put it in front. I have the leaf C0. I have the node X5, node Y6, and then the node Z2. Now in the operands, you saw that it was actually in the, if I want to be really faithful, I have to put the coefficient at the very end. So let me do this. So I put the coefficient at the end. So this corresponds to the list of operands. So the label is the multiplication. And in a way, this is not entirely a recommended way of working, because you see I made a typo. So the labeled order tree is misspelled. Unfortunately, I made only one type error. So this is the first term, and I can continue. So in a way, it is a little bit tedious, but I think it's a very good exercise to explore the tree structures. So the next monomial, perhaps I can see this. No, this is still from the. So what is my next monomial here? So let me select it. So I can copy this over. So it's the second one. So it's Q1. So that's the monomial. So you see I have already the y6 sitting in there. So it looks very horrible, but actually it's not that horrible. So I have the operands. So if I want them in the right order, then you see that the coefficient also appears last, and the operator is again a star. So what I can do is I can copy and paste this entire code block and start adjusting. So I don't need to define actually the z anymore, and the y neither. So these are the leaves that I don't need. I need the coefficient 3 when I want the node x3. So I don't need 2. I need one coefficient, and that's the minus 35 over 2. I have already the leaf z, so it will go faster than I had anticipated. So I have the x to the power 3. I have the, sorry, so here the leaf 6 should be the leaf 3. This should be x, this should be 3. So I have y6 was already defined. I have the leaf, the symbol z, and then I have the coefficient. And this gives me my second term. Okay, so Q2, the last term, Q operands. I select the second one. And here I'm actually lucky that it is a shorter term. So I do need x to the power 5, and I have not yet defined the x to the power 5, I think. So, or I did. So that's even not needed. I need the z to the power 5. Z to the power 4. So that's leaf 4, and I don't think 4 was defined. So leaf 4 and leaf z. And the coefficient is 2 over 9. So the operands, perhaps I should skip this step. So if I want the right order, see if I want the right order, then the coefficient again comes last. I have the node z4, so I have x to the power 5, the node z4, and then I have the coefficient leaf, and that is my second term. Good, so I have three trees, term 0, term 1, term 2. So I can now assemble the final expression tree. So it's a labeled ordered tree which has three children. I call them term 0, term 1, term 2, and the operator is the sum. So it's good not to forget this. We had three operators and I have not yet used the sum. Here you see the final expression tree for this polynomial. So this final expression tree is another way to represent a polynomial. We have seen the ways to traverse this polynomial when I discussed the fast callable trees. We had the in-order traversal, where you first visit the left, then the node, then the right. We had the pre-order, where you see essentially first the operator and then the operands. And then we have the post-order, which corresponds to the stack evaluation. This applies not here with the stack evaluation, so I should probably emphasize that. So here, the way the expressions will be evaluated symbolically is by applying an operator on a list of operands. So here we actually see the pre-order traversal. So let me make that point. In the symbolic evaluation of the expression, we apply the pre-order notation. So that means that we have for every operator we have a list of operands. So we see the plus operator as the list of the operands. So here we had the sum of term 0, term 1, so probably I will not. Plus is the operator. And then we had the term 0, term 1, term 2. So that's one way to see this. Okay, so let me return to the binary expression trees. So the fast callable objects. So you may have wondered why we call them fast. Let's experience this now. Let me make a fast callable object. So in this section, we use the expression Q to make a fast callable object. And what is actually important is that this will indeed lead to a faster numerical evaluation. So making the point that fast is indeed what it is saying. Okay, so from SageMath ext miscellaneous import fast callable. So let me see if I did this right. No, I didn't do this right. So let me check this. So the fast callable should actually not be imported. Okay, so the fast callable is actually there. So I can immediately make a fast callable object of Q. Well, I thought I did. So the list of the variables must be expressed. So if I make a fast callable, then I must say what the variables are. So perhaps I should probably copy and paste this over from the preparation. Okay, so now I have my fast callable object and I can test this. So I will call the fast callable on a numerical input, and I actually don't have any better numbers than 1, 2, 3. So this is the numerical evaluation. For the symbolic evaluation, or actually to evaluate the symbolic expression, I'm using the keywords way of doing this. So by the way, for those who are familiar with Python, in Python one can define callable objects. So that means that one has an object that one can treat as a function. And that is essentially what the expressions in Sage are. They are callable objects, so you can use them as functions. So here I substituted the formal parameters. I replaced the formal parameters x, y, and z by the numerical values. So I'm interested in fast, but first and foremost, I'm interested in correct. So you see, with the numerical evaluation and the symbolic evaluation, I actually get the same result. Okay, is it now really faster? Well, let's time it. So when I do time it, I pass the string. And you see that with the fast callable, it takes about 23 microseconds. So, and many loops were needed. Oops. So let me do the substitution now. So I will time and there you see that the difference is significant. So it's 100 microseconds. So already and microseconds are actually instantaneous. So 625 loops were needed to actually see some difference. But you see already for an expression as tiny as our Q, the fast callable actually matters. Now the point, of course, is that with a fast callable, you can only do numerical evaluation. Now it depends on your point of view. If numerical evaluation is all you care about, then do use a fast callable. So the general expressions are actually still much more flexible as far as evaluation goes. So they support substitution, something that we will see in a later lecture. So let me now look at the binary tree. And actually here I want to finish. So I can look at the list, the stacker representation. So here you see that everything is binary if one asks for the operation list. So the last thing that I want to show is the representation of the expression as a fast callable expression. So this is the stack. So we see the stack of operations for the fast callable. Let us turn the expression Q into a fast callable object. To see into the binary expression tree via the fast callable. Okay, I'm still have time, so actually what I wanted to show was the expression tree builder, and I was starting to type this in, and so let me make one attempt. So the expression tree builder. So, and I should have known this, there is not this module. So it's the extension fast callable. So, and I will a bit, for convenience, I copy this from my preparation. So I will do again a symbolic evaluation, and actually I will evaluate again the polynomial, the original polynomial I begin with in this lecture. So, and this is again the symbolic evaluation, but now I take the symbols of the expression tree builder. So I make an expression tree builder, and I'm saying that the letters that I'm going to use for the variables will be the strings x, y, and z. The x, y, and z here are the letters, the variable names that I'm using to respectively address these three variables x, y, and z. So I will make an expression tree builder with three symbols. The variable names where I can refer to these three symbols are called x, y, z. So there is a difference between now the string representations, the variable names as they are in the expression tree builder, and the variable names in the session. So the symbolic evaluation takes the formal xyz, so this is yet another xyz, and replaces the formal names by the variable names that refer to the variables in the expression tree builder, and then they are written as the letters x, y, z. Okay, so the point is that with the symbolic evaluation, of P in the context of the fast callable expression tree builder, we see the binary expression tree for P, as would be convenient for a numerical evaluation. So we are, so with this, this expression tree builder, as it is here, is only useful for numerical evaluation. And what I did on the slides, so it is still here. I'm not sure if I will be able to create an overlap. Perhaps I will be. So if I shift this up and somehow it doesn't work that well, but let me try once more. So this might be better. So what you see is the expression here. So at the very top we have the add. So this is for the entire expression, but start reading here from the multiplication. So this is the multiplication that corresponds with this star. We have the coefficients minus 1/2, which is here, and then we have the two multiplications for the monomials x to the power 5. Will it work? So x to the power 5 and y to the power 6. So it does work. So very good. So here you see the binary expression tree for the first term, as one can read off from here this part. So this corresponds to the, I don't think I can highlight this, but so that's the main point. Okay, I'm running towards the end of the allotted 50 minutes normally for a lecture. So the point, the main point is that we distinguish between symbolic and numerical evaluation because of the elementary numerical arithmetical operations. They are binary. Our fast callable expression trees for numerical evaluation are binary. But that's a very specific case. So in this course on symbolic computation, we are often more interested in general expressions which have non-binary expression trees. Okay, I hope that this pre-recording was interesting, and I thank you for watching.